My name is Brian Eklov. I'm a member of the Kalamazoo American Chemical Society group, and I brought something fun to show you guys today. I have air, but in an odd form. I have liquid air. What I have here is liquid nitrogen. So nitrogen is 80% of the air that we breathe, and normally I don't think anybody here breathes liquid. You normally need gills for that. And this is what liquid nitrogen looks like here. Liquid nitrogen is liquid because it is incredibly cold. Minus 340 degrees Fahrenheit, 77 Kelvin. It's very cold. It has a couple of very interesting properties that way. So we keep it, because it's so cold, in these little styrofoam containers because they're very convenient. You can get them at the store. Liquid nitrogen is a little harder to get your hands on. But because it's so cold, it has some very interesting properties. The first of which is one that I think most people are familiar with. Is that things that get colder change shape. You know, if you take a balloon like this one, this is a very nice National Chemistry Week balloon, and we cool it down, we would expect to change. And because the balloon is full of air on the inside, as it gets colder, it reaches something that looks more like that liquid state. I can show you this real quickly because you saw how big my cooler is here. It's about the size of a balloon, and I've got a couple balloons here. And it's a lot of fun. We could do this all day. We could just keep putting balloons in here and keep making them disappear. But because you can hear the crackle, I think, because what is in the balloon is mostly nitrogen. When we get it exposed to the liquid, it gets cold. And what happens to the air in the balloon is it shrinks. And so when it warms back up again, it will re-expand. So you can see our poor little balloons shrunk, and then when you take them out and let them warm up, they usually regain their shape. Every once in a while, one of them pops because it doesn't. The rubber that makes up the balloon gets hard when it's colder, and so sometimes they pop. But we can do that again. Shrink them, warm them back up. It's very. It's fun. So the reason why that happens is when things cool down, the motion of the atoms slows down. They don't move as fast, they don't move as far. And the balloon is the size and shape that it is because the gas on the inside is pushing out on the balloon the same as the air in the atmosphere is pushing back down on it. But when we cool this down, the air on the inside slows down, cools down, it can't push as hard against the inside of the balloon, and so it shrinks. When we warm it back up, the atoms move faster, the molecules move faster, and it returns to the state it was in before. So we're going to cool a couple other things down to talk about some properties. It takes a minute, so I'm going to go ahead and get that started. I have a racquetball. It's just a standard racquetball. And I have a banana. And we'll give those a few minutes. So you can see the gas escaping the side of my cooler here. Maybe this is a better way to see it. What you actually see here is not the nitrogen. It's actually water vapor. So the water vapor in the air, as the cold gas comes out the side of the cooler, it cools the air that's in this room, and the water vapor condenses out. So what we have here is a little cloud. And it's kind of fun because you can usually see it roll right over the edge of the table, and we can get a little cloud waterfall going here. And of course, it's headed down towards the ground because the nitrogen is cold, and so it's a little denser than the air in the room, and so it falls towards the floor. If this were full of helium, liquid helium is fun because it's even colder than the nitrogen. But the helium would head up towards the ceiling because it's less dense than the air. But the nitrogen is more dense. All right, we need to add a little bit more here and keep this cold. We can show you another example of how things get colder as they, how molecules move differently when they're cold. And so I'm going to bring on a volunteer here to help me with some flowers. This is Julia. Julia, which one of these is your favorite? You like flowers, right?
Yes.
That one? All right. Could you do me a favor?
Yeah.
Make a little room here. Could you just tap that on the counter? Did you notice anything interesting?
No.
No? Okay. Would you mind dunking that flower into our vat of liquid nitrogen there? Ooh.
It is pretty cold.
It is? Do you want gloves? Let's put gloves on.
Smoke is cold.
Do you want to wear my awesome oversized gloves?
Yeah. No,
So these gloves are used to protect hands against the super cold liquid nitrogen. That's why they're so big and fluffy.
Also
They're like super winter gloves, right? Huge.
oversized.
Oversized is right. All right, so could you do me a favor? Pick that up and tap that on the counter again. Tap it. Little tapper. There you go. So do you notice something different about your flower this time?
It's dead, basically.
It's brittle.
Yeah.
Yeah. And that's, again, thank you, Julia. May I borrow my gloves back?
Yes.
So what happens is the flower, even though we don't normally think about it this way, the flower is mostly water. And so water is a liquid at room temperature. You can see it warms up pretty quickly. But when we cool that down, that water in the flower freezes, makes ice. It becomes brittle. It's no longer a liquid, it's a solid. And that makes the flower brittle. And you can hear the difference. So I have a helper here with me. This is Adam. Adam likes to help with construction at home. And so we have a very special task we need to complete today.
Okay.
We have this nail.
Okay.
We have this block of wood.
Okay.
We need to pound this nail into this piece of wood.
Do you have any hammers?
I have a banana.
That's not a hammer.
It's a banana. It's what we have. We're going to make do. So could you try that again, please? You're getting banana on my nail. This is not working.
No, it's not. It's a banana.
Okay. All right, let's try something else.
You killed it.
Yeah, it's had a rough day. Okay, could you put those gloves on for me, please?
Yeah.
Okay. I have a banana that we've had in here in liquid nitrogen for a few minutes.
Still.
It's still a banana, but it's a very cold banana. There we go. There's my banana.
That banana does not look very structurally stable.
Are you ready? I need some help here.
Which part of it?
I don't care which part. I think that's good. It worked, right?
I scratched your banana.
Thank you. Can I have my gloves back?
I guess.
When we froze the banana in the liquid nitrogen, it's very cold. It's no longer mostly liquid water, as a normal banana is. It's mostly solid water. And that really, you can hear the difference, right? Because it's frozen, because it's so hard, we can actually use this as a hammer now. And we were successful in putting the nail into the 2x4, where we were not so terribly successful with our other banana. All right, I have one more for you. Julia, could you put the gloves on, please?
Yes, sir.
Adam, can you come help me one more time?
Sure.
So I've given Adam a racquetball. I'm sure you're all familiar with the racquetball.
Hey, these gloves are so cool.
They bounce well. They're designed to. It's rubber, it's soft, you can squeeze them, it's pliable, and it bounces nicely. I have another racquetball that has been in the liquid nitrogen here since we started. I'm going to hand this one to Julia. And guys, what I want you to do is stand with the ball out. Yep, Adam, other hand, please, so that you're facing each other. And drop. That is the first time one has broken in a very long time. That's awesome, Julia. I didn't know you had the strength. So what happened? The molecules in the racquetball that Adam has are warm. It's elastic, and it can bounce. The other racquetball didn't bounce because it couldn't flex anymore. It had gotten so cold that the molecules wouldn't move, and it shattered rather than bounce. So those are the experiments we have for you today. Liquid nitrogen, it's very cold, minus 340 degrees Fahrenheit, and shows you some of the interesting properties and interesting things that happen to household materials when they get that cold.